Okay, good morning. So we're talking about circuits, and last time we got to the first concept, that circuit concept that's useful and that you need to know how to apply. So here is a little example. Very simple circuit. We have one component, just one component. The rest of the circuit I have not drawn yet. Good. So now you're introduced. I have not drawn the rest of the circuit. Just one component, X1. Question, how much power does component X1 dissipate? Well, it's got to be 3, right? And it's also got to be 3 watts. But is it plus 3 watts or is it minus 3 watts? Plus. And why is it plus? How would we go about that? So what is the first thing we have to decide? Yeah, exactly, the sign convention. Is this the way I've drawn the plus and minus and the arrow? Is this passive or is it active sign convention? It's active sign convention. And then in the active sign convention, we need to know, is the power voltage times current or is it minus voltage times current? Minus voltage times current. So the answer is correct. It's plus 3 watts. This component actually dissipates power. So it's minus 3 volts. So this is because it's active sign convention times 1 amp is equal to plus 3 watts. Okay? So this could have been, if we had done a quiz today, this could have been on the quiz. So previous lecture, we went over this, I explained it. I thought it was pretty straightforward. Maybe you didn't. Then you can come to the office hours, you can read in the book or so. When I go over a concept like this, next time expect that you understood it or you raised your voice and you said, no, I don't. Explain this better. Okay? Nothing more complicated than this. Now we're making more complicated. That would not be on a quiz. Okay? What comes now? All right? So just sort of that we get calibrated. Okay? So make it a little bit more complicated. Let's say there is another component here, X2. And just to make it even more fun, there is a component X3. And let's say I also know the voltage here, 2 volts. And now I want to know what is the power of component X2 delivered. Okay? How much power does component X2 deliver to the rest of the circuit? So now this is a little bit more complicated because we have to invoke 2 different concepts that we both learned in the lecture before, but we have to combine them together. So that would be fine on the homework, obviously, but I wouldn't assign something that complicated in a quiz, just the lecture after. Okay? So again, to get us calibrated. All right, well, how would you go about this one? I didn't understand you. Now I have even more difficulty. I need one of these focus beams so that I can home in. Well, maybe somebody from further back. How would you go about this? Yes. Okay, the first thing we need to find the voltage across X2, and how would you do that? Okay, yeah, we use Kirchhoff's voltage law, so why don't we do that? How we apply Kirchhoff's voltage law? We draw a circle first, so like this. There is only one possibility here. And then when we write the law here, we enter on the minus sign, on the left side with component X. I can't point to my screen here, doesn't help you, right? We enter the component X1 on the minus side of the minus 3 volts. So the first component is minus 3 volts. I draw this in purpose so clumsily so that you can see exactly. And then, we have to assign here a voltage. Let's call this voltage V2. Okay? Plus V2. We enter on the plus side, and then plus 2 volts is equal to 0. And from there we get V2 is equal to minus 5 volts. Huh? Right? Did you do it right? Okay, so what's the current running in X2? Well, it's an amp. Now is this equals minus 5 volts. Is this passive or active sign convention? Here it's passive, right? So for component X1, the arrows and pluses and minuses worked out here to be active sign convention. For component X2, they worked out to be passive sign convention. You got to look at every component. It's not that you can say, well, you know, I don't like this active and passive. That's two different things. It's too complicated. I'm always going to use passive for whatever, right? You can't do that, right? For every component, it comes out whatever it wants to be. Conveniently, when we have a choice, then we usually use active sign convention for sources, and we use passive sign conventions for elements that dissipate power. But, you know, it doesn't have to be that way. And here we don't even know whether X2 is a source or a dissipative element. So here it's passive sign convention. We want to know the power delivered. How much is it? So it's minus 5 volts. I can't write here, times 1 amp, minus 5 watts. Sorry, my handwriting, but I really can't write at the edge of the screen. Okay, so here we get actually minus 5 watts. That's the power. Oh, wait a second. Yeah, because minus, then it's plus 5. So this one actually delivers positive power for these numbers here. Okay. Make sense, this example? All right, so we will need that kind of thinking on the homework. Okay, so let's go on. This is actually a copy of my energy bill here, electricity bill. And the thing that I want to... Yeah?
Can you go back to the previous example?
Sure. Sure.
So the power is flowing down to the negative sign. So what is that power times voltage? So 1 times negative 5? Or am I just getting really confused?
Okay, you're talking about component X1 or X2?
X2 and V2. Component X2.
Component X2. So we want to know how much power does component X2 deliver. So then we have to first determine whether it's active or passive sign convention.
So here we have passive sign convention.
Okay.
So it's voltage times current, right?
Yes.
So voltage is negative 5, current is 1, so shouldn't it be negative 5 watts?
Okay, but in passive sign convention, the amount of power that the component dissipates is plus voltage times plus current. Okay? Whereas the amount of power that the component delivers to the rest of the circuit is minus that. I made the same mistake that you made, and fortunately, people paying attention, but we need this extra minus sign here, okay? So this minus sign here is because normally we would, if we had used power delivered, if we had used active sign convention, then we wouldn't have this minus sign. But then, of course, I would have had to draw the V2 the other way around to get active sign convention. And then V2 would have been plus 5 volts instead of minus 5 volts, that other V2, right? Okay, any more questions? Yeah, it's important. Thank you for interrupting me. It's important that you get this because these are the simple things that I will just assume, unless I make a mistake, that we will just use this and we'll just plow over it, and you need to understand that and to be able to follow and learn material, okay?
Can we find the power for X3 and find the power for X2 from X1 to X3?
Yes, of course. So the question is, now that we know the power in X1 and X2, could we find the power in X3 simply from knowing what the power in X1 and X2 is? Could we do that? Yeah, how? Exactly, the sum should be 0. Now, we have to be very, very careful because, of course, if we add these up, that's not quite right? We have to be careful. For example, we calculate the power of all, we sum up all the power of all the components, what they dissipate. So that would be let's say the first one, X1 dissipates 3 watts. Then the component X2 dissipates how much? Plus minus 5 watts. And then plus the component X3 dissipates P3, okay, equals 0. So then we can figure out P3, which is the power that component 3 dissipates, would be equal to 2 watts. Okay. All right. So yes, we can do that. And now, of course, you can also, we see here the current that goes through X3 is 1 amp, passive sign convention. So 1 amp times 2 volts is 2 watts. Oof, we did this right. Okay. So in fact, I encourage you to do stuff like that, and we will have many more ways. I will show you, for example, about 3 ways to analyze circuits. They all are complementary, so there are reasons why I give you 3 ways. But one benefit you get if you have 2 different ways to solve a problem is that typically on my exams, most students have more than enough time. Time's not the problem, usually. Okay? Then, rather than looking at the problem and making 3 times the same mistake in your head, go and solve it 2 different ways. And then if you get a discrepancy, you usually can find out what's wrong, right? I promise you can. That's how you go from an A minus to an A plus, or A to A plus, or B to B plus, or whatever, right? So stupid mistakes, if we eliminate those, that's usually more than half a grade point. And of course, it's also important because imagine, right? I mean, that famous bridge, if we make a mistake there, it's pretty fatal. Okay, so, and the circuits that we build, usually people do not get killed, except if it's power circuit, high voltage. But nevertheless, it's better, right, if you don't make mistakes. It's not so good. Okay, so this is my electricity bill, and it's kind of hard to read, but here it says total usage 109 kWh. What does this mean? Yeah, so it's actually kilowatt hours, and so it's not just kilowatts. Why not? What does it mean that I've used 1 kilowatt, for example? That would be the power that is flowing at any time. Let's say a kilowatt. Well, that would be an electric cooktop on very low heat, or a small space heater, right? Would be a kilowatt. It's using that while it's turned on, but of course I got to pay for how long that thing is turned on and using a kilowatt. And so what I really pay for is energy. And energy is simply power times time. And the SI unit for energy is joule, or watt seconds. That's the same thing, although when you enter it, for example, in this automatic grading system for the homework, you got to say joule. You can't say watt seconds. It's not smart enough to say, oh, that's actually the same thing. You know? Just not that clever. And then you can do. Then there are other units like watt hours. The electricity company likes this unit better, and it's obvious, right? Yes, if I have, for example, iPod 100 watts and I let it run for an hour, well then I consumed 100 watt hours. It's very easy. I could, of course, convert this to joules, and I've done this here. 1 kilowatt, that's 1,000 watt times 1 hour, that's 3,600 seconds. So 1,000 times 3,600 is 3.6 million joules. Watt seconds or joules. Okay? So just the energy unit. That's what we pay for. And so maybe energy is the 4th unit. Joules is the 4th unit that we often deal with in electrical circuits. So energy is very, very important. So there are tons of different units. Other people, they like to use TNT, and Cal, of course, is a unit also, even though it's also the name of the best university in the world. We know all that. But then there are yet other units. If you have a car, then maybe a fluke once at your battery, you have to replace it. Of course, It's most likely it's going to be 12 volts, but then it says something else. It says, this one says 54 AH. What does that mean? Amp hours. Amp hours. So is that an energy? No, it's not an energy, but we can calculate the energy really easily. So that's really, amp hours is current times time, and to make it energy, we have to multiply with the voltage. Now we've got energy, right? So we have to take the 54 amp hours, multiply it with the 12 volts, then we get watt hours, and we can, of course, convert that again to joule. So that would be 2.3 megajoules. So could I have, what did I use there? You used 109, no, even more than that, 109 kilowatt hours, and then every kilowatt hour is 3. My car battery would have been more than emptied many times last month if I had used it to supply all the energy that I needed, right, on my previous build. Okay, anyways, that's yet another, amp hours is yet another sort of bizarre way to express energy, but it's very convenient. That's why it's used often, and I think there is a homework problem, and so now you know how to do that. Lots of interesting things about batteries, and so just one aspect that I put on here, right? Battery is always the problem. Why is it the problem? Well, we never can seem to be able to bring enough juice along to run all the gadgets that we would like to operate, right? And so people have been working on making better battery technology, and they've been partially successful. They got a little bit better. They also got sometimes more expensive, for in general, batteries tend to be one of the more expensive pieces that we need in our systems. And so here are a few metrics that are interesting about a battery. Of course, the first is the cost. How much does it cost per watt hour? A battery where I can store an energy equivalent to 1 watt hour. So in other words, I can draw 1 watt from that battery for an hour. That's not a whole lot. I couldn't run, for example, this project and uses probably about 300 watts or so. Couldn't run that off such a battery. Anyways, for lead acid, where is lead acid used? Yeah, that's the car battery, right? That's the old, clunky, famous car battery. That watt hour cost me just 17 cents. If I use a lithium-ion battery, I pay over $4 for that. So why would anybody who is good in it, his or her mind, pay $4 when he can get the same thing for 17 cents? Yes, I'll give you a chance. Yeah. Well, even in your laptop, who has a laptop that has a lead acid battery? Huh? It would be just watt hour per kilogram. It's 41, and for the lithium ions 128. So you just carry 3 times less weight around if you use lithium ion. But what about electric cars? Who has one? Me neither. They're way too expensive. Huh? But what do they actually use? They use lithium ion, all of them? Maybe, yeah. But I mean, the cost of the battery apparently equals the cost of the car, right? And you can see easily why that is. Of course, if you make it out of lead acid, it would be a lot heavier. And then you would have this big truck, and would just barely be able to carry you around, assuming that you haven't eaten breakfast, right? So, there is. Here is the same thing, joules per kilogram, watt hours per kilogram. We know now, right? We don't need both columns in the table. We can convert it ourselves. But watt hours per liter, look at here, it's different. Per liter, that means how big is this thing, right? And so here, actually, nickel magnesium hydride is actually better than lithium ion. So if you want it really small and you don't care about the weight, well, you have other choices. And plus, it's 4 times less expensive. So we are not going to talk a whole lot about batteries, and so it's more an issue of chemistry or so, but of course we are users of these, and so I thought it would be interesting to just briefly talk about this. Alkaline, incidentally, alkaline is very good, but of course you can't normally recharge it. And what else? What about the power outlet? Well, we could calculate, right? If you paid attention on the previous slide, actually, it was like 12 cents per kilowatt hour. That's how we pay for the electricity that comes out of the outlets. So now, of course, we could convert that into dollars per watt hour. I have to divide by 1,000, and so we get $1,000, so that would be 3 zeros, 1 per watt hour. So the power out of outlets is very, very inexpensive. So, of course, this isn't really fair, the comparison, because you can charge a battery many times. Right? This is just the cost to install that battery power. It's not really the cost of taking that energy out. So if you can use the battery 1,000 times, and then you just have to pay the cost to charge it and so on. So it's not really a fair comparison. But still, I mean, cost of power out of batteries is expensive. Okay? So what else do we have here? Oh, a little example. So let's suppose that you have a little cabin, and it's in a really nice spot, but unfortunately it's off the grid. So you have a car battery there, a 12-volt lead-acid battery available in your cabin that maybe you'll load with a solar cell, or maybe you have a small hydroelectric power plant out the back door. And now you want to do your EE40 homework, and it's a little bit dark, so you need to turn on a light. And you have these 20-watt halogen lights that operate off of 16 volts. So first you have a little problem, right? Your battery, 12 volts. The halogen lights, 16 volts. How are you going to make it work? Well, you need some kind of a booster, some kind of a voltage booster. And lo and behold, we're going to design this one, but not just yet. Okay? Later in EE40, we're going to build some kind of a contraption that takes 12 volts and makes 16 volts or any other combination of voltages. Okay, but before we do that, we just want to know now how long, assuming we had that contraption, how long will that battery last to power that light? Will we be able to complete our EE40 homework, or will we need another battery? Okay, so how would you do that? Yeah, back there. Okay, so first we want to know how much energy do we have in the battery. So that's how much? Well, that's 50 amp hour times 12 volts, right? That's the energy in the battery. And then we know that energy is equal to power times time, so we can solve for power, for time is equal to energy in the battery divided by power. So that would be this, actually it's 2.2 megajoules, I've calculated this beforehand, divided by 20 watts, and this comes out to be approximately 30 hours. I hope you don't need that much time for the homework. Okay? Incidentally, I did extend the due date for homework 2, but I encourage you to finish it by tonight, simply so that you get Labor Day off. Okay? But it's your choice. Okay, so high voltage is dangerous, as you can see. Did I pay you? Okay, high voltage is dangerous. So these are just a few things that I pulled off the web. Right? You can, of course, start a fire with high voltage, and this is a particularly stupid thing to do. Right? There is high voltage. I touch it, stretching out my arm. Well, it still can kill me. Actually, there are about 500 deaths, electrocutions per year in the US, so people who somehow do a foolish thing. That's not an extremely large number, but nevertheless, 500, of course, it is dangerous. So why is electricity dangerous? What is it really in electricity that kills? Right now we have 4 different numbers that we can use to describe electricity. With we have voltage, current, power, and energy. Which one is it that actually kills? Current? Well, if you had a large current that would flow for only 1 femtosecond, would it kill? Would it do anything? No, it wouldn't do anything, right? It's really the energy that. It's true. I mean, probably if you have 1,000 amps flowing, because it takes a little time to ramp up all the way to 1,000 amps. We'll see that later, why you can't turn on 1,000 amps in just a femtosecond, probably. But nevertheless, if this time would be very, very small, then the energy delivered to your body would be so small that it just cannot do any damage. Okay, so with 1,000 amps, granted, it's probably impossible to do that. So 1,000 amps don't get it through your body. But here are a few examples of. So let me put it that way. In order for electricity to kill, it's the energy that has to be sufficiently large, and for that, this product has to be large. So if we can make one of these quantities in this equation small, really, really small, well then maybe the total energy is small enough also. Okay? Yeah.
What is given energy to a person killed?
Actually, you know, I tried to look it up and I couldn't find it. You know?
I don't know specifically, but I know that for some very short time, getting as little as couple milliamps across your heart is lethal.
Okay, yeah, so again, that doesn't really tell us what.
From what I know, it's like, you know, when you have a brain,
Okay, we'll get a little bit more to that, and so we can say maybe yes.
So like, if you just have like 1 milliamp, like 21 volts for 50 years, you're not going to die.
Yeah, well, yeah, not exactly. So there are. So let's look at just a few examples on that might and decide about them, whether they kill or whether they don't kill. So static discharge, right? Sometimes you touch something and actually, if it's a dark room, you actually see a spark flying. So what does the spark flying indicate? Yeah, exactly. It indicates that V is really, really large, but probably the static electricity is not very. The static electricity stored in whatever you touched isn't very large. Why not? No, it's because of that same thing where we, in that homework where we calculate if you try to separate electrons, well, they really don't like that, right? If you get positive and negative charges, you get forces and so on. You get all sorts of conditions that really try to get rid of that situation. Now, if you have something big enough, like if you have the the atmosphere and the Earth, and you have the charges in between them, then you get lightning, right? And there, the power could be, so that's actually an example here. There, the total energy could be very, very large. Why do people not always get killed from lightning? Well, because our body isn't exactly a conductor, right? And so maybe the current doesn't actually go through our body. Okay. An electric fence is for cows and so on. How much voltage do they use? I once designed one. It was like 20,000 or so. Okay. Yeah. So, but again, what you do there is you load that voltage on an inductor, and we'll look at inductors later, and you make sure that the energy that inductor can store is very, very small, and therefore the energy is smaller than what is required to really hurt a person or a cow, for that matter. I've mentioned that in the CPU of your computer, that even in your laptop or so, when it's running full blast, the current that's flowing may be 50 amps. If you open up your laptop and the current is 50 amps, you touch around in there, will you get killed? No, right? Maybe you can get burned because the CPU can get terribly hot, more than 100 degrees, but Celsius. But the voltage is going to be very small, right? Maybe a volt or so. Birds on an electric wire, you know, they sit on the high voltage wires. Why do they not get killed? Why don't they all fall off? Yes. Exactly. I mean, they sit on the voltage across the wire is everywhere the same, roughly, right? The drop hopefully isn't very large in the wire, and they put their feet on there, and well, I mean, they are now their potential is now 300,000 volt with respect to ground, but their feet are not long enough that they can have one on the wire and the other one all the way down 20 meters or so. Okay, so. Lightning, right? Again, it really depends on where the current. The energy certainly is large enough. The voltage is large enough when we have lightning. The question is where the current goes. So sometimes people have burns. Sometimes, of course, they get killed. So again, I can't really tell you. I'll look. Maybe I can find it, but I don't know how much energy is really needed. Probably also depends on where the energy goes, right? If I, for example, run a really large current through my arm, it's going to fry my arm, right? And I'm not going to try it. But it's not going to kill me, right? My arm will be totally burned. I will not be able to write anymore, also, but doesn't kill me. So burns. So the first thing, what protects us is that yes, our skin isn't a conductor. In fact, if our skin is dry, then the resistance through our body over any reasonable stretch or so of skin is on the order of kiloohms, right? But actually on the order of hundreds of k-ohm, okay? When it's dry. But when it's wet in a bathroom or so, or humid, then the resistance of our skin decreases substantially. Then we have salt ions and so on that allow current conduction. And then, of course, with the relatively modest voltage, we can have a decent amount of current flow. And so that's why in the bathroom it's so much more dangerous to play with electricity. And so there are really a number of mechanisms where electricity can be dangerous for us. The first is the simplest one, just burns, right? If I have enough current, enough voltage, enough power and energy, well then, it's like a cooktop, right? So that's not good. Usually that takes quite high voltage, usually more than, quite a bit more than 100 volts, several hundred volts for that to happen. You cannot burn yourself with just 10 or 20 volts, the battery voltages or so. Then there are ways to get your heart or other muscles to act up, and one of them is if you touch the 50 or 60 hertz and suddenly your heart locks to that frequency, and that is not very good. Also, if the current gets fairly large, several hundred milliamps, then your muscles contract, and that's very unfortunate because you can't let go, right? Normally, if it tingles a little bit, of course, you want to let go, but then you still want to let go, but your muscles contract and you have no control over them anymore. And then there are neurological effects where somehow your brain or whatever, your nervous system is taken over by currents that come from outside. That's obviously also not very good. So that gets us to lab safety. So not next week, actually next week, all you have to do for the laboratory is you have to do the first pre-lab. It's put up on the web, so you have to go through all these questions. You have to answer those by Friday next week. So before the lab, before you go to the lab, you already have to answer a whole bunch of questions so that you're prepared to do the lab. So here we are just going to quickly talk about lab safety. So obviously we have power outlets in the lab, and these power outlets, they carry 110 volts. In some labs they carry 220, and we never touch those, we never use those directly. In fact, we have wonderful instruments like, for example, the lab power supply that sort of puts something between that dangerous outlet and us, and then on the other side of the lab power supply we have lower voltages or so that are not dangerous. So in fact, obviously don't stick any of you will have plenty of probes and wires and so on. You could stick those into outlets. You're old enough not to do that, right? So, okay, so then all the experiments that we do in this laboratory in EE40, they use voltages less than 30 volts. At that point, the skin is a very good protector. There is pretty much no way that you can get hurt with that. But there are some experiments. I told you that we will, for example, build something that goes from a low voltage and makes a higher voltage. In fact, I think the experiment is set up so to go from 5 volts and make 15 volts. Anybody knows how to do that? No, it's DC. It's out of battery, 5-volt battery, whatever, right? Yeah? No, you can't do it with a transformer, no, because it's DC. What? Yeah, exactly. Yes? Camera circuits? Oh, that's right. That's right. Something like that. In fact, there are clever things in there, inductors and capacitors and so on. Somehow you can do that. So that gives us something to look forward to. We'll get there. It's possible. So one of the experiments is a boost converter. We design it that it just puts out 15 volts from 5 volts, no problem, right? But don't redesign it that it puts out 1,000 volts and then have problems, right? Obviously. Even though you will know how to design it to make really high voltage. If you have any questions also, obviously, ask your instructor. You can also use the voltmeter to go and check a voltage before you go and touch something, right? Generally, in the EE40 lab, it's designed in such a way that you don't need to do that. But, again, if you muck around with this, you're not sure. There are ways to. And then the main thing is, if you use common sense, nothing's going to happen. But obviously, always, you need to use common sense. Okay? So, what did you go over here? Well, we looked at branches and nodes, the circuit elements and wires. We introduced all sorts of ways to describe electricity, current, voltage, power, energy, and their units. Kirchhoff's laws, we're going to use these all the time, and then these passive and active sign conventions, something else that we'll just rely on, use. Okay, are there questions? I could. The lab schedule, yes? Yes. So doing a laboratory, in general, that has nothing to do with just EE40. When you go to the lab, before you even put your foot there, you need to know what you're doing. One reason is safety, right? I mean, some experiments, they could actually be dangerous, and so you need to think about that first before you enter the lab. And then the other thing is, doing things in the lab invariably take a lot more time. Designing a circuit on paper, with pencil and paper, or maybe running a computer simulation, so if you make a mistake, yeah, it takes some time to fix it, but not that much. In the laboratory, when you make a mistake or so, it takes you a lot of time to fix that, or if you're not prepared, it takes you a lot of time. So you have to really know what you're going to do in the laboratory before you go there. Otherwise, the 3 hours will be over and you will still be wondering what you actually want to do. So because of that, for every lab, there is a write-up that you can download from the web. So Lab 1, I posted that yesterday. And it describes what the lab is, it describes what the goals are, and it asks you to design various circuits, or to figure out what the component values are in the circuits, and just it tells you in general how to do the experiments. So this part is called the pre-lab, and you do that just like an assignment. You fill out your answers into boxes, you submit it to this online system, and it tells you right away whether you are prepared for the laboratory or not. Okay? And there again, the same thing as for assignments. If you have questions or so, come to the office hours and we'll help you with that. And that's always due the Friday before the week when you actually go to the labs, right? And so depending on which lab session you are, your lab may be on Monday, and so there's just a weekend between submitting that pre-lab and actually doing the lab. And for others, the lab may be actually only the Friday after, and hopefully you haven't forgotten everything. And then in the laboratory, you do all the experiments, and generally there are boxes again, and even sometimes graphs or so, where you put all your measurement results right into that report. And that time you don't submit it online, but you actually print it out. You give it to your TA at the end of the lab. It's done in such a way that if you're organized, at the end of the 3 hours, you're done with that lab. You've done everything, you've learned what you need to learn, and yes?
Do we need to bring a computer to that thing?
There is a computer in the laboratory. Okay? So you can bring your own, but you can also use the one that's installed there. Okay? So you hand that in, and we'll get that return. But it's very important that you do these pre-labs. So this coming week, laboratory, it's like a homework, right? You get prepared. And by Friday, you got to turn it in. Okay? Any more questions about the lab? So perhaps a little bit different in other classes where you have labs, you have to have lab books and so on. That's a very good thing, because normally later when you work on your own, there is nobody who sort of structured what exactly the experiments that you need to do in the laboratory, and so then the lab book is important. However, in EE40, I decided that I want to make the labs that you do a little bit more things, but then I give you a little bit more help with the organization so that you can do a lot of things in just 3 hours and be done with it. So try to use it that way, that you efficiently. All right, so we already got some mileage out of Kirchhoff's laws, right? We can make schematics, we can have circuit components, we can measure or somehow using Kirchhoff's laws the voltages and currents. And but there is one problem. The components, they really didn't do anything, or we didn't know what they were doing, and there is nothing that links current and voltage. So for that, that's the job of the circuit elements. So we're going to talk about these circuit elements now. So one thing is that there is just an unbelievable number of circuit elements that is available. That's some vendor, a web page, and in fact another vendor that we're going to use for the project. From that vendor's DigiKeys website, you can purchase order over almost 500,000 different ports, right? So, and I've listed some of the ports that you might that you could get there, and obviously there are many, many more. So we got to be organized somehow about this, right? EE40 is not about learning 450,000 different things. Okay, so how does circuit design really work? Well, okay, I made a mistake. Well, I can tell you what I wrote here, that you can see what. That is really clumsy. So what we do is circuit design really is sort of one art form of composition. And what do we mean with composition? Well, in circuit design, what we use is a relatively small number of different element types, like batteries and resistors, so that we will talk soon about. And then we arrange them in the right way to create complex behavior. And I'll give you a few examples for this. Well, a few component types, and then we arrange them to get complex behavior. Okay, so examples. Today, supercomputers are no longer that important. Why? Well, because we all have a supercomputer. What would have been 20 years ago a $20 million machine, well, now we can have it on our desktop or in our laptop, right? But anyways, there was a man, his name is Seymour Cray. And he had just unbelievably good idea. He always made the fastest supercomputers. And so he actually made a company called Cray that still exists. It's no longer as important because supercomputers are no longer that important. But anyway, this man Cray, he designed supercomputers. So these are very big machines. They contain millions of ports. How many different kinds of ports do you think he used in order to implement the circuits that made up his supercomputers? How many different kinds of ports? Obviously, there are individual ports, there are many. 4 or 5? Something like that, yeah. Yeah, actually, mainly there are 2. There was a NOR gate. A NOR gate, and we'll talk about what the NOR gate is, but anyways, it's one circuit component. And there was a memory. Just two circuit types, and he arranged them the right way and made a supercomputer out of them, and then he sold it for like $20 million or so, and he sold many of them, right? So using composition out of just a small number of simple parts, we can make something very complex. Another example would be, this actually stands for operational amplifier. It's a part that in about a week or 2 we're going to talk about. Operational amplifier. It's a circuit component, and hey, not too surprising, it can amplify, but it can also be used to sum, to compute differences. It can be used to filter signals. It can be, what did I write here in addition? It can do impedance transformation, whatever that is. It's something important, but it can do that. Right, so one part, it also is the basis for a gazillion different homework questions or so. One part we can really do all sorts of different things about. So once we understand that part, we can do a lot of things. Actually, today's chips, they're often called CMOS chips. So almost all the chips in your handset, almost all the chips in your laptop, also these computer chips, they're so-called CMOS chips. What does CMOS stand for? Complementary metal oxide semiconductor technology, but the complementary really means that there are just 2 types of elements. There are 2 different transistors. One of them is called NMOS, and the other more. So there are two. They're called NMOS and PMOS, and if you go and look in a computer chip, for example, has 1.2 billion parts, then just about all of them are either this type of transistor, NMOS, or they are PMOS transistors. That's all there is. So it's just composition. You can do these elements are a little bit more complicated than these NOR gates, for example, but if you understand them well, and we'll start understanding them a little bit, then you can do all sorts of different tricks with them and get interesting behavior. Okay? So, but now I wish you a nice Labor Day weekend.